Welcome to chapter 7, number 21, and in our problem it tells us we have a light spring with spring constant 1,200 newtons per meter, and it's hung from an elevated support. From its lower end, a second light spring is hung, which has a spring constant 1,800 newtons per meter. An object of mass 1.50 kilograms is hung at rest from the lower end of the second spring. So we're given that K1 equals 1,200 newtons per meter, K2 equals 1,800 newtons per meter, and our mass is 1.50 kilograms. And what we need to find is the total extension and then the effective spring constant. So let's start with part A. I'm going to draw a real quick figure. So we have our first spring denoted by that, so that's going to be called K1. Our second spring right here, K2, spring constant K2, with a little mass here, 1.50 kilograms. If we look at it this way, let's just look at the second spring. So we need to balance out of forces. So mg, which is 1.50 kilograms times 9.8 meters per second squared, is equal to kx, which is 1,800 newtons per meter times delta x. So what is delta x? So we're going to calculate that. So delta x, we're going to put this in our calculator. 1.5 times 9.8 divided by 1,800 newtons per meter. So it's going to be 0.00817 meters. Or we can say that's just 8.17 millimeters. Okay, so that's the first part. And now what we should realize is that second spring down here, say these are my two springs now, it's being pulled down and it creates this restoring force, but there's also the same restoring force on the other side, right? So this one is also going to have to balance out. So we're going to have K1x also equal to, or I'm going to call this K1x1 equal to K2x2, because it's different displacements technically, equals mg, right? Because this was equal to mg. So now we can just set that one equal to mg. So we do the same thing, 1.50 kilograms times 9.8 meters per second squared equals 1,200 newton meters times delta x2. I'm going to label this as x1 up here real quick. Okay, so delta x2, let's put this in our calculator. 0.5 times 9.8 divided by 1,200. Ooh, so that's a whole 0.01225 meters, or that is 12.25 millimeters. So our total delta x for part A is a sum, so I'm going to add that to, we're going to round it, so we'll say it's 20.4 millimeters. And whatever units you want to use, you could also use 2.04 centimeters, or you could just say 0.0204 meters. So that's our answer. And for part B, it tells us to find the K effective. So what's the K effective? So we take our total displacement, right? And let's just say we treat this as a whole spring. This whole thing is one spring. We have our same mass, mg. So then we have K effective times our delta x total equals mg. So now we plug this into our calculator. Over 0.0204. So 1.5 times 9.8 divided by 0.0204. We get 720. So 720 newtons per meter. That is our K effective. And you didn't see that. So then let me just recap. So you get K effective times delta x total equals mg. So I just put that. M is 1.50 kilograms. This is 9.8 meters per second squared. This is 0.204 meters. We get 720 newtons per meter. And an interesting fact about that is that this K effective if we take the reciprocal, equals that. And you guys are going to learn about this relationship later. But it is called series. Alright, so that's K effective for series. Thanks for watching.